Let's imagine there is a 200-gram block of mass 1 hanging from a pulley, and a 50-gram block called mass 2 also hanging from the same string over the pulley. So what is the acceleration of the pulley? What's the acceleration of the blocks that are pulling on the string? Well, Francine thinks that masses will accelerate at 9.8 meters per second squared because the only force acting on them is gravity. Fred thinks that the acceleration will be less than gravity because they also have a force of tension that's going to be pulling against gravity and slowing them down. Let's see who's right. This problem is an example of what's called an Atwood machine. And an Atwood machine is when we have two masses, or 2 points, mass 1 and mass 2. We have a non-stretchable string, so we can consider that that tension in the string is not going to change. And we have a frictionless pulley, so we can ignore the friction in the pulley. So let's see how we can find the acceleration of the blocks. We're also going to find the tension in the string, because this is something we may need for other problems. The first thing you need to do on these problems is draw a free body diagram, and we're going to draw one for each mass, mass 1 and mass 2. We're also going to define our coordinate system, our positive and negative x and y values, so that the acceleration of the string is going to be positive in the same direction for both. And I'll show you how that works as we do this problem. So first, we're going to draw our free body diagram for mass 1. Mass 1 only has the force of tension pulling up on it, and it has the force of gravity pulling down on it. Now we know that mass 1 is 200 grams and mass 2 is 50 grams. So once we let go of the system, mass 1 is going to go downward and mass 2 is going to go upward. So we're going to define our coordinate system that even though normally we would say down is negative, we're going to say that down is positive because that is the direction that our system will accelerate. So we have gravity going down, and that is going to be defined as positive. We have tension going up, that's defined as negative. When we get to mass 2, we have tension pulling it up and gravity pulling it down. Now for mass 2, we want the acceleration direction to match mass 1. So for mass 1, we said that going down is positive. But this string, if it goes down on this side, it's going to go up on this side. So on mass 2, the up direction is going to be positive because a positive acceleration will pull mass 2 up and it will pull mass 1 down. So for mass 2, we define up is positive and down is negative. Our force of tension goes up and our force of gravity goes down. Now that we've defined our free body diagrams and our direction for positive for the acceleration, we're going to write our net force equations for the two masses and we will solve them. We'll start with mass 1. Sum of forces in the y direction for mass 1 is the force of gravity, and so that we don't get confused, we're going to call it Fg1 because it's for mass 1 and we don't want to confuse it with Fg for mass 2. And that's going to be positive because we define down as positive. And tension going up is going to be negative. The sum of those forces is going to be mass 1 times the acceleration. Now the acceleration is going to be the same for mass 1 and mass 2 because they're connected by a string. They will accelerate at the same rate. So we're just going to define A. We don't need A for 1 and A for 2 because they're going to be equal to each other. Now we're going to plug in some values. For the force of gravity of 1, it's mass 1 times gravity minus the force of tension equals mass 1 times A. We can put in our numbers because we have a mass, and we can put it in both parts. We're still going to end up with an equation that has two variables, force of tension and acceleration. But this is our first equation that we'll use. We're going to isolate the variable tension. We're going to rearrange the equation and get tension by itself, and the force of tension is 1.96 newtons minus 0.2 kilograms times acceleration. So now we have our equation from the first mass. Now we're going to get our sum of forces for mass 2. For mass 2, in the y direction, we have tension, and we defined up as positive for mass 2, minus the force of gravity of 2 going down. All of that added together equals mass 2 times the acceleration. And as I said, this A is the same as this A. Now we can replace Fg2 with mass 2 times gravity and plug in our values. And we will get the equation force of tension minus 0.49 newtons equals 0.5 times A. Now, between these two masses, they're on a string that doesn't stretch, so the force of tension is going to stay constant. The force of tension pulling on mass 1 equals the force of tension pulling on mass 2. F sub t can be replaced with this equation here, because the force of tension doesn't change. So we're going to plug that equation in right here and then just finish the rest of this equation. Now we have a problem that only has one variable, and that is A. We can take A, we can get it by itself by doing some subtraction and division, and we get an acceleration of 5.88 meters per second squared. So Fred was right. Acceleration is less than 9.8 meters per second squared. And that's because we had a tension pulling against the force of gravity. Now we're going to find the tension in the string. Well, we found A is 5.88 meters per second squared, and we had originally found this equation for mass 1, which related acceleration to tension. So now we're just going to plug our acceleration in, and we can solve for tension, and the tension in this string is 0.784 newtons. Let's consider another problem. We're still going to have a pulley, but now we're going to have one mass that's sitting on a table and one that's falling down. We have a 20 gram mass hanging, which is mass 2, attached to a 250 gram mass on an air track. That means there's going to be no friction. We want to find the acceleration of the system and the tension of the string. Now, there is a mass pulling down and there's no friction, so we're going to see this whole system move. Mass 1 will move to the right and mass 2 will move down, and we will use that information to define our positive axes when we draw our free body diagrams. So let's do our free body diagrams. For mass 1, the only force acting on it in the x direction is the force of tension. There's no friction slowing it down. We know it's going to accelerate this way, so we'll define to the right as positive. We also have a normal force and a force of gravity for it. For mass 2, our force of tension goes up, but we know it's going to accelerate down. Since it accelerates down, we'll define down in the y direction as positive for mass 2. That's going to be the force of gravity, and then going up is the force of tension. Now we're going to write our sum of forces equations and solve. So for mass 1, in the x direction, we're going to look at force of tension. The sum of forces in the x direction is mass 1 times the acceleration. In the x direction, we only have the force of tension. So force of tension equals mass 1 times acceleration. We can get a simpler equation by putting in the mass. Now we're going to use that by looking at mass 2. And for mass 2, we're looking in the y direction. Sum of forces in the y direction is mass 2 times acceleration. Make sure you make your force of tension negative because we defined it that way, and your force of gravity is positive. Force of tension minus force of tension plus m2g equals m2a. Now we can put in the values that we have for mass 2 and for gravity. Solve this so that we are down to having the variable tension and the variable acceleration. We're going to take this equation right here and combine it with this equation. So there's our two equations, and we're going to find A first. We're going to put this value into force of tension in the second equation, and we're going to solve for A. And we get A is 0.726 meters per second squared. Once we have A, we can plug it into the first equation to get the tension. And we get tension of 0.181 newtons.